Okay, so I'm just going to introduce Professor Tavoularis. Thank you all for coming. Professor Tavoularis is kindly accepted to be here and give us a talk about the idiosyncrasies of the dimensionless dissipation parameter in turbulent flows. Professor Tavoularis is the recipient of the prestigious George Glinsky Award for Excellence in Research, as well as the Medal of the Canadian Congress for Applied Mechanics. He's a fellow of the Canadian Academy of Engineering, the Engineering Institute of Canada, the Canadian Society of Mechanical Engineering, as well as the American Physical Society. He received his doctorates from the Johns Hopkins University, and he's been a faculty at the Department of Mechanical Engineering at the University of Ottawa for over 4 decades. I don't want to give away any age information, but basically before I was born.
I don't hide anything.
No. Currently, he's served in the past as department chair, interim vice dean of research, and the director of the Ottawa Carleton Institute for Mechanical and Aerospace Engineering. Now, a lot of you may, who have taken my course on experimental fluid mechanics, probably already have heard of Dr. Tavoularis from his exceptional textbook, Measurements of Fluid Mechanics. And he is currently the director of the U Ottawa Fluid Mechanics Laboratory, where his research continues to bring insight to the fields of turbulence, turbulent mixing, vortex dynamics, aerodynamics, thermohydrodynamics, as well as biofluid dynamics. So with that, I will leave the floor to Professor Tavoularis. Thank you so much for coming, and I look forward to the talk.
Thank you very much, George. I'm very glad we continue contact with you after so many years. It's quite convenient to give this talk online. Of course, I am still in my home office, but I hope to have an opportunity in the near future to visit you and meet you at your workplace, as well as your colleagues and your graduate students. So, what I will talk about today is a topic which is a classical topic. It has been in the forefront of research for quite a while, but it's by no means resolved, and we are looking forward to some future breakthrough that will advance the field of turbulence research and turbulence modeling. So the title is On the Dissipation Rate of the Kinetic Energy of Turbulence. If you are not familiar with the theory of turbulence, you may not recognize immediately what these words mean, but I will try to go through all the definitions and have some introductory discussion on each concept, so that people will understand what I'm talking about. Otherwise, it becomes a bit tiresome, to hear many terms there. So this is the outline of my talk. So first, I will identify different types of turbulence that we see, from the practical to ideal and in between. And then I will introduce the topic of energy dissipation and the rationale behind scaling energy dissipation and the consequences of that. And then I will show some experimental results of measurements of this dissipation parameter, a scale type of dissipation in different types of turbulence, and how to use them for any future purposes. And I'll just close with a brief summary. So I identify 4 types of turbulence, and I will spend a little time talking about each. The practical one, the one we see around us and in industrial or technological processes. Then we move to a conceptual level of turbulence, which I call the ideal turbulence. I'll introduce what are the what is the rationale for doing that, and how it is connected to other types of flows, and then some intermediate categories between the practical and the ideal. Canonical, which is a term that has been used for a long time to describe flows mostly of academic interest and created in laboratories. And then a term which I have introduced, a multi-structure turbulence, which is again some intermediate type has some intermediate structure. So to start with the practical examples of practical turbulent flows in real world, in recent years, we all became highly interested in the pathogen transmission, particularly through exhaling, the droplets that carry viruses and other types of pathogens. And this is a concept of turbulent diffusion, how far this can be transmitted, how long it can be, and so on. If we look at our cardiovascular system, the heart and large arteries have flows which are characterized as turbulent, at least during part of the cycle. Not exactly the same as other turbulent flows, but nevertheless, the term applies to some degree to them. Then in our environment, of course, flows in the atmosphere and the ocean are generally turbulent and highly turbulent. Also of technological interest, we have in power generation, in this particular case is the wind turbines, but any kind of power plant would have a large number of turbulent flows of different fluids. In transportation, we have, of course, many other issues, aerodynamics and transportation, safety, economy of transportation, pollution generated by different means of transportation. And of course, issue of pollution is very much connected to the properties of the turbulent flow that creates that. So this is the real world. But now I'm gonna have a few things about which are closer to philosophy rather than engineering. So we talk about ideal turbulence, and I go back in early philosophers. Plato, you have heard, he had this theory, that expressed to great detail through dialogues, that for every object that exists in reality, there is the substance of this, what you call the idea of the object, and in Latin, this idea is translated as ratio, the one I have here. So I created a pseudo-Latin term to describe the idea of turbulence. That is something conceptual, and the point that was made in this presentation of any idea is that in order to gain knowledge, we have to understand the nature of this idea, because when we look at practical things, we may be distracted by specifics, this. But if you want to gain insight into the concept, you have to idealize it and isolate it from other complications. Okay, so in this sense, the physical world is a projection of this Platonic world, this ideal world, which is again a conceptual world and cannot be materialized. And then I'm going to try to say what is the essence, what is the nature of this ideal turbulence. And again, I put some Latin term here that I made it up. Really, these are not established terms anywhere. And the idea, you may have heard something on the nature of things. This was a book written by an author, Lucretius, who was an Epicurean philosopher around 1st century AD. And in this book, he tried to explain, and he gave detailed explanations of any physical phenomenon, the phenomena of life, and trying it includes the state of the art of the science as a means of explaining our world around us and what's happening. And he talks about atoms that they were uh, already at the time used, as a model of the material world. About thinking, about he even has details about Brownian motion, molecular motions and so on. So this is the nature of things, and this is what I'm talking about. Okay, so the nature of ideal turbulence. What are the characteristics of ideal turbulence? First of all, geometrical purity. So to have a very, very idealized geometrical property, such as unbounded flow, that you don't have the complications of boundaries that are happening, complex geometries and so on. So we talk about ideal. We are not concerned about specific geometric complexity. Next level is statistical simplicity, because turbulent flows are random. All properties in turbulent flow, they are random functions of location, of space, and time. Okay, so we need to use statistical simplicity. For example, homogeneous. That means the properties, statistical properties, averages do not depend on location, right? And there are other approximations and simplifications. And the last thing is dynamical supremacy. I make this term. What does this mean? It means that the turbulence mechanism is by far dominant to any other complexity that is coming from additional effects, boundary effects, other interactions among particular types of other flows or other influences, such as, for example, phase change or mixing, of different fluids and so on. So dynamical supremacy means that the mechanism that generates the turbulence and the structure of turbulence flow is idealized to the limit as turbulent activity goes to infinity. And this is characterized by this value of a Reynolds number. It's called the turbulence Reynolds number. I will define it in some other slides later. Because you can define Reynolds number in different ways using different length scale and different velocity scale. In this particular case, you use scales which are relevant to the turbulent structure itself. Okay, and that Reynolds number, ideally, for ideal turbulence, should go to infinity. So, of course, this is not attainable in any practical or realistic flow, but people have put a lot of effort for a long time through experimental work or even computational work, computational analysis, to reach as high as possible values of this Reynolds number, because when you try to validate some theory that applies to ideal flows, right, to infinite Reynolds number, let's say in principle, but you test it in a case which by necessity will be some intermediate Reynolds number. And if the theory or the model you have does not work very well, you can say it's nothing to do with the model. It has to do with the fact that our test case does not reach the value of the infinite, or the Reynolds number is not large enough. So there has been kind of a competition about among different experimental groups worldwide, in different places, very strong researchers, multiple participants and so on, to try to push the limits of different types of examples of turbulence towards this ideal case. But obviously, this is something we can keep pushing, but will never reach the limit of infinity. So in other words, this is a case such as the example I have here, the pursuit of ideal turbulence. I put as a parallel to the Holy Grail, that you are looking for the Holy Grail, but it will not be found. So this is the kind of infinite Reynolds number goal, to be able to reach that and find it and so on. Okay, so now going back, leaving the philosophical aspects and going back to reality. So we identified practical cases, so I put them down to earth. For example, a practical example is an industrial mixer. that you put all kinds of things inside and they are mixed in a turbulent environment with all kinds of complications, solid boundaries, blades, perhaps phase change, multi-phase flows, all kinds of things, right? So that's a real flow. And ideal one is we extract, out of that only the essence of the turbulence. And we take a case, for example, an unbounded flow that allows some mixing there. And we start the mixing in this case. And we can say homogeneous means not depending on location. The statistics do not depend on location. And I add the term isotropic. Isotropic means that the statistical properties are independent of orientation. So if you take an average, let's say in the vertical direction or in some horizontal direction, they are not affected by this orientation. Okay, so now this is quite far from the practical case, so that's why I left a large gap in between, because we can understand quite a few things by studying the ideal problem, but to what degree can this be applied or are relevant to the practical problem? And I have another example, the environmental example. You have a wind over a city with the buildings around, and could be additional complication, precipitation. It could be solids being transported, leaves, things, which distort the fluid and so on. And an idealization of that is a pure two-dimensional boundary layer. Okay, that does not have the other complications. And again, a lot of effort has been put to create these in laboratories, also to study them by very precise computational methods, the direct numerical simulations. So quite a bit is known about that. And there is a legitimate question: how much of this is relevant to the practical flow, or can be applied directly, or what we need to go to convert this knowledge into the practical use. So there is a large gap between the two categories, and this contains a class of flows that have been characterized as canonical flows. Canonical flows are somewhat in between. They are generally created in laboratory. When I say laboratory, it could be also computer laboratories, numerical simulations. They're relatively simple, not as highly idealized, but relatively simple. And they are amenable to scaling. So once you create some regularity in these flows, you can see that you can do some normalization of properties, variables. For example, distances can be normalized by some thickness or some length scale, and velocity by some other scale, and so on. And you can produce certain solutions which are of fairly not completely general, but of more wide type of applicability, and we learn a bit more of that, and we can actually apply these a bit closer to practical problems that can be approximated by this kind of thing. And so the one main characteristic of these flows is that the turbulence is under some control, the production of turbulence, and typically would be generated by single mechanism. There are many mechanisms that can produce turbulence. One is the shear, the non-uniformity of the velocity, or an average velocity gradient, if we can say. That is capable of producing random fluctuations and turbulent eddies and so on. There are other effects, buoyancy. For example, in the atmosphere, you have warm or cool currents moving up and down, and they generate turbulence. There are centrifugal effects. There are other mechanisms, and it could be that there are multiple mechanisms of the same kind, of different kind, and they produce. But these generally are not going to end up in a canonical flow. So typically, we have a single production mechanism. So much of our understanding of the turbulence has been achieved through the study of these flows, and there are textbooks, and there's still progress in those, but there are classical things. The wake, the mixing layer, the grid-generated turbulence, uniformly shear turbulence, boundary layers, jets. There is a number of flows and a few more complicated. So much of it is known. And in fact, when we develop theories and models of turbulence to be of more general use, we need to validate those, and the validation to a large degree is done on this type of canonical flows. You also need to tune up. You have numerical adjustable coefficients, and you try to say what is the optimum value of this coefficient, and you tune it up to fit some data, mostly those generated in this type of canonical flows. At the same time, do we see many of them anywhere in reality? And the answer is no. It would be very rare to see one of these flows in its controlled kind of form in an application, either technological or biological application or environmental application. And so there is still a gap between these flows and the practical flows. Okay, so this is what I see. So I put some canonical flows in between the other two. These are flows created in the laboratory very carefully, you know, and with control of different properties. And I have two examples: the grid-generated turbulence and the turbulent boundary layer in wind tunnels, and the equivalent of numerical studies, direct numerical simulation. So we bridge the gap to some degree, not entirely. And here comes the relatively new thing that I thought it is appropriate, which I call multi-structure turbulence. And the multi-structure means that the turbulence is produced by more than one mechanism, and these mechanisms are interacting, and they are complicating the turbulence structure. And practical flows may contain many of these mechanisms. Here we isolate two at a time and try to see how does this mechanism affect the structure of the flow by comparison to a canonical flow. And you could have two canonical flows interacting with each other, and the structure will be different from each one of them. But how different it is, does it relax back to a canonical thing, or what's happening to that? And this is a case of intermediate complexity between canonical flows and practical flows. And I have a few examples that I'm going to talk about how to produce a multi-structure turbulence. So one way is to distort a canonical flow by a second mechanism and see how much this distortion affects the structure, and whether, if this distortion goes away, what is the rate of relaxation back to canonical case, or if it doesn't go away, how does it lead perhaps to a new type of structure, you know? So this is what I'm talking about. Okay, so I'm not sure what time am I supposed to finish. Could somebody give me a time frame? George?
Just hello. Yeah.
Yes.
Sorry, the mute is stuck on my end. The seminar students usually leave at 2. So if you want to leave some time for questions, maybe a little bit
okay.
before.
So I'll try. I may go a little faster through some, or I may skip a couple of slides. I don't have that many slides, but okay, that's why I have to time myself. Okay, so the energy dissipation. Okay, we start with the mathematical analysis. We need to write the governing equations, which come from the basic principles of conservation of mass, or we call continuity, and Newton's second law, which we call the momentum equation. So in differential form, as you see, continuity is written here, and you see there's an index I, U is the velocity, X is one of the 3 coordinates, and the convention is called the Einstein summation convention. If an index is repeated in a term, it means this is summed. So this is the sum of 3 terms. So that's the continuity. And I take a simple case of incompressible Newtonian fluids, such as water or air. The momentum equation, Newton's second law, can be written in this form. And the left-hand side is essentially the acceleration, total acceleration written in this convention. Then you have the pressure term, the pressure force, and the viscous term, uh, which describes the effect of friction. Nu is the kinematic viscosity. And if you look at this equation, this has a free index, ui. That means there are three equations. Momentum are three, u1, u2, and u3, the three directions in a Cartesian system. So there are four equations with four unknowns. The unknowns are the three velocity components and the pressure. So it's what we call a closed system. You have four equations and four unknowns, and you specify appropriate boundary and initial condition. You should be able to get a solution to find this field. So this applies to any flow, whether it's laminar or turbulent. But in turbulent flow, because of the randomness, it's meaningless to solve this equation, and you find a function of position and time, which will change very rapidly. And so also, how are you going to store all this information, and how do you process? So what we do is we average things out. So like any statistical, any random variable, we apply some statistical analysis to bring something manageable, to extract out of these random processes. And so we can average, and the typical case in turbulence used widely is the Reynolds decomposition, where this is the instantaneous velocity at one point is written as a sum of an average. These angle brackets mean an average plus a fluctuation. The fluctuation has zero average because all the averaging goes here. So that's same with the pressure. So if we apply this to these equations, you see this term here I put in red is a nonlinear term. It's a product velocity times a velocity derivative. And when you decompose, and it would be, it will translate into four terms. So there is additional unknowns that are generated by this. And when you do the statistically average equation called the Reynolds average equation, you see it differs from the previous one by the last term, the red term, which did not exist before. It represents a turbulent property. And this term, ui, uj, has three values on each of them, but there are 9 terms, but 3 of them are identical to 3 others. So there are 6 additional terms. So we started with 4 equations, 4 unknowns, and now when you apply averaging, you get 4 equations and 10 unknowns. So this is definitely an open system of equations. It cannot be solved. So how do we solve it? One way is to say, what if we write additional equations? Okay, let's write equation for this term. Then you open a huge can of worm. You can write equations for that, applying statistical ways. That's manipulations of equations. But anytime you put a new equation, there will be many more unknowns, another order of magnitude of additional. So you are not getting to solve the problem by putting additional equations, which are proper equations coming out for first principles. So the other way is to do to put some empirical equations. Okay, empirical means based either on some curve fitting into some experimental data, or to have a theory and say there should be a relationship between the different unknowns, and put some connection between, for example, the Reynolds stress and some of the other terms that appear in the equation, such as the mean velocity. So if you can connect this new unknown to the other 4 unknowns without introducing additional unknowns, then the problem can be resolved. And so this is what we call turbulence modeling, okay, which is used extensively. There are other approaches to the turbulence study, but this is still, and for practical problems, turbulence modeling seems to be almost a necessity, because you can attack real problems without excessive resources, and it's possible to get something out of this. And the question is, how accurate is the prediction of this kind of thing, or what kind of model is optimum for a particular problem? Okay, so An example of a simple model there for this one is what's called the gradient transport model, which connects this Reynolds or turbulent stress to the mean shear. And there's a coefficient here that's called the eddy viscosity or turbulent viscosity. So this is a model which is analogous to the Newtonian fluid, where you have the shear stress is equal to the viscosity or kinematic viscosity times the mean shear, right? That you have the mean strain rate actually. So, but in this case, this eddy viscosity is a property of turbulence. It depends on the turbulence activity. It's not a material property. The viscosity is a property of the fluid. So if you have water at 20 degrees C under standard atmospheric pressure, you know the value. You go to a table, you know, that has been, data have been tabulated, and you get a value. It's not an unknown. But in this case, this is an unknown. So you change the problem by introducing another unknown, and this unknown has to be connected to something, and you have to at the end close the system to produce enough equations or relationships to make it solvable. Okay, so if you express this eddy viscosity, I'm talking about the simple model here, whatever you express it in terms of has to appear in this equation and has to be resolvable by these equations. Okay, so how do we produce new equations? So one way is to write equations for the turbulence itself, the turbulent stresses, the Reynolds stress tensor, or the sum of the three stresses, the total turbulence activity, which we call the turbulent kinetic energy, and it's normalized per unit mass. So this K term, you heard perhaps the K epsilon model. So K is the turbulent kinetic energy, and epsilon is the dissipation rate of the turbulent kinetic energy. So this is a half of the sum of the three normal stresses, and represents how much strength the turbulence has in terms of fluctuations. So the turbulent kinetic energy equation can be derived directly, and you get an exact equation that's as valid as Newton's second law and so on. But it contains a lot of new unknowns there, and some of these unknowns need to be modeled, and they are routinely modeled. But there is an additional equation. So if you manage to express all terms instead of the models, or some models that do not introduce additional unknown, then you don't make the problem worse. You move towards producing a closed system. So what does this equation have? It has a term on the left-hand side, something like the acceleration, but we call it the rate of energy, of change of kinetic energy. Is the kinetic energy growing or decreasing in time? Okay, so that is the left, and then it's equal to the right-hand side, which is the balance of this term. There is a term which is always negative. Okay, and that's called the dissipation of kinetic energy. So what happens is turbulent motions have relative velocity. Different parts of the fluid move with different speed. So one moves faster than the neighboring one. So there's friction between the two. The same way when we rub our hands on a cold day, they get warmed up because part of this friction that between the two hands, which means we can call the shearing, right? The shearing means the relative velocity is converted into kinetic energy of the molecules, right, in our hands, which is we call heat. As this kinetic energy increases, the temperature increases and we warm up the hands. So this is what happened. Part of the mechanical energy of the turbulent motion is converted into thermal energy, means increase of temperature. Now that increase of temperature will be extremely small, it's not even measurable, but nevertheless, it's a sink of mechanical energy. If that's always there, no matter what flow you have, the friction will always be there, there will be a dissipation. What about replenishing of this energy? That kinetic energy can be produced, for example, by the mean shear, the mean velocity gradient. Okay, so you have production, you have dissipation. And in general, you have other terms. The other terms do not introduce a net increase or decrease of kinetic energy overall, but they represent transport of kinetic energy from one position where it's high to where it's low, or in different directions. You can have activity more in one direction and this converted into activity to another. So we are concerned mainly about the production and the dissipation. Okay, so we have one more equation now. We have 5 equations, and the dissipation also can be treated to have an equation. Say, why don't we have an equation for that? And it's possible to derive, but that's a completely hopeless. Instead of that, we can write an ad hoc. That means we mimic the kinetic energy equation. We write an equation for the dissipation rate. So we can introduce an additional term. And now we need to model the various terms that appear in these equations, and there are models that have been developed over the years, and there are still improvements and extensions and updates of these and more tests and so on. So that is what happening. So we close the system and we have, and now how do we produce the scaling? Okay, so the scaling of turbulence, we have, if you look at all these equations, everything is per unit mass. That means the mass does not appear as a parameter. Okay, and so the only dimensions that appear in this equation, all the terms, we have velocity and we have distances, x, x1, 2, 3, and time. These are all have dimensions including length and time. Okay, now if you look at the velocity, velocity is length over time, so it's equivalent to say that we need scales of velocity, of length and time, or we could use scales of length and velocity, because from those two you can get a time scale. Okay, so we need to have these, and these scales, it will be some physical scales. We need to identify them, and they should be part of the solution. So when you get a solution of the system of 6 equations, you have to come up with those scales too as part of the solution. 6 equations for the mean velocity and mean pressure, and these scales too, the 2 scales. So they have to, somehow you have to relate those scales to the equation. Now, let's try to identify these scales. First of all, there is an obvious turbulent velocity scale, which is the square root of kinetic energy. Okay, this is a term that appears in the equation. And then what we use for length scale, the size of turbulent activity, there are physical eddies, let's say, the motion, turbulent motions is the physical side. There are some of them which are dominant. They have most of the kinetic energy, and therefore the size of those motions is a relevant scale that we should use for the problem. But that scale, typically we can call the integral length scale, is by integrating correlation. To get the size of the eddies, you have 2-point values. You take a distance between 2 points and see how far you have to go until the relationship between the 2 activities at the 2 points dies out. Okay, and that gives you a size of this eddy, of this turbulent motion. But this is a 2-point activity. You need to write equations for multiple points, which we don't have. Here we have single point values. Therefore, that length scale we understand is the appropriate one, but we cannot connect it to those statistical equations. Okay, so that is the point. How are we gonna do? We have to invent a different scale that somehow can be connected to the variables that we already have in the problem. Okay, and so we do that by dimensional analysis. Let's try to find some other length scale which is relevant to this problem and appears or is a combination of properties in these equations. And first of all, we have to say, what are the primary variables? When we do dimensional analysis to scale a problem, we have to take the scales, right? The primary variables, which are they have certain dimensions, and those dimensions of the primary variables can be combined. You take every property that appear in equation to be product of powers of these primary variables to some exponent, and you adjust the exponent to produce the dimension you want. To produce, for example, a velocity or a length or a time or a velocity square or velocity cube, whatever you combine them. Okay, so the three primary variables we can use, one of them is turbulent kinetic energy. The second is the friction represented by kinematic viscosity, and the dissipation rate. These are the choices that appear in the equation. But if you look at these, each one of these includes length and time. So to extract a single scale of velocity and a single scale of time is not possible, because you have three. You have infinite combination of those that will give you a length and a time scale. And so you have to select, either combine only two of them, or if you combine three, you have to select one out of infinite choices of how you collect them. So, and this is what I say here. So what are the length scales that are used in turbulent flow? One is the so-called Kolmogorov microscale, in which case you do not use at all the kinetic energy. You say this is a property of only the very small motions. Okay, very small means whatever happens in the large scales is irrelevant. It's only very small, and this is where the dissipation occurs. The friction is most effective at a very small scales, where the relative velocity dissipates energy, kinetic energy, into heat. And this, if you disregard the K, you end up with this scale, which is called the Kolmogorov microscale, which was introduced by Kolmogorov in 1941 and is still used extensively everywhere. Then if you have you want to use all three, there is an intermediate scale. Out of many choices of combining of the exponents here, you select one choice that gives you this combination, and that includes all three variables. And this is called the Taylor microscale. And this is the size of some intermediate type of scales, not too small and not too large. And then you can also have say, okay, now let's eliminate the viscosity. Let's go strictly to the large scales where friction doesn't play any role. And you combine the K and the epsilon, and you get another kind of length scale, and I call it the surrogate macro scale. Clearly, eta applies to very small motions. That script L, or calligraphic L, applies to large energy containing motions, and then you have the other one in between. And so the question is, does this script L connect to the physical scale, the Roman L, which is the appropriate scale of the large turbulent eddies? And this has been connected to the concept of energy cascade. Now I have to go a bit fast, so I'm going to skip quite a bit. If you have not seen that, so this axis, the wave number is inverse wavelength, is inverse size. So the large eddies, the infinite eddies, have wave number of 0, and the extremely small eddies have a large wave number. Okay, so this is a spectrum in log axis. So it tells you how much activity, this line tells you how much activity is associated with a certain size of turbulent motions. The turbulence has a continuum of sizes of motions from very large to very small up to a certain level where they cannot be any smaller because their energy is dissipated into heat. And there is production typically at a large eddies by the geometry and the boundary conditions. There is production of the activity, and that's where it's produced. That's the source of energy. At the very end, there's a sink of energy. And for intermediate eddies, there is a path of transfer of energy that large eddies transfer energy to smaller ones. And if the Reynolds number is large enough, this range here in logarithmic scale is over many decades. So you have a large range of orders of magnitude over which this happens. And this intermediate range where a turbulence is neither produced nor dissipated is called the inertial subrange. So it's possible to connect now the dissipation dissipation, which is a very small scales, to the production, because all the dissipation is fed by the production. And so the point is, the dissipation rate epsilon is connected to the large eddies because through this mechanism, because that's the source of all the energy that's dissipated, although energy is not dissipated at the large eddies. Okay, so okay, I think I have to skip quite a bit. So how are these related? So we take the ratio of those two scales, the physical scale and the surrogate scale, and typically if we substitute the dimensional the combination of powers we have for that, this is what we call the dissipation parameter. Okay, and this dissipation parameter now is, if it's equal to 1, it means the two are identical. If it is constant, it means they are proportional to each other. But the question is, how can we say that? Is it true or is it not true? So this is the question, and this is what I'm trying to address here. Okay, so, and how does this apply to different types of flows? The ideal flows, the practical flows, and anything in between. Okay, so the dissipation model that is called the cornerstone assumption of turbulence theories and models is that C epsilon is constant. And so essentially all turbulence models and theories start with this assumption. And this is what I'm questioning now. Is this assumption valid? Because it's an ad hoc assumption, means we just made it. It's not an empirical result that they put together all kinds of measurements and they found that it is true. Okay, so, and I question that. So, okay, I have to move on. Okay, so which types of this turbulence? Now, ideal turbulence is some sort of equilibrium. It has infinite Reynolds number. So presumably this kind of assumption is valid, but this turbulence doesn't exist. So even if it is true, what's the use of that? And then say, okay, what if would it be true if we increase the Reynolds number and we have any kind of flow with a high Reynolds number? And that has to be tested. Okay, is it true or is it not true? What about canonical flows? Canonical flows have some regularity. Would it be true that they have a constant C epsilon? Or all turbulence we have. I mean, it would be great if any kind of turbulence has a constant C epsilon, but until we test it, we don't know about that. Okay, so let's first show some example in canonical turbulence. Okay, these are some of them from my lab, and many others people have done it for a long time. Okay, so this is C epsilon, the ratio of the two scales, and if it is constant, it means this. So this is what we call grid-generated turbulence, and we see at high enough Reynolds number, this is relatively constant. We have here C epsilon. This is distance from the grid that you have the where turbulence is produced, and we see there is a part where C epsilon is not constant, but there is a part that's constant. So there is some evidence that this C epsilon is constant in at least part of the grid turbulence. It's true also in a flow that has a uniform shear stress. And again, if you look, I have a C epsilon here. Let me see, where's the C epsilon? Here's C epsilon. This is distance from the origin. You see it settles at a level which is essentially constant over a certain range. So what is the conclusion out of these canonical flows? And I have some results for boundary layer, is that in canonical flows, there could be a region where C epsilon is constant, and we can be confident that this kind of theories and models would be appropriate for that. What about multi-structure turbulence? I have two examples here, recent work. One is a flow that has a constant shear and then is distorted by a grid. And so right behind the grid, there is a region of disturbed uniformly shear structure where the flow is multi-structure turbulence. And there is a region there where in this multi-structure turbulence, if you look at, okay, let's look at this one, this slide here. right? C epsilon versus distance. You see this green area is the multi-structure region. C epsilon downstream of that reaches back the level of canonical grid turbulence or canonical shear flow. But in the multi-structure turbulence, dissipation parameter is much larger. So we cannot apply this type of assumption to the entire flow, particularly not in the multi-structure region. And another example I have here is a boundary layer, right? The boundary layer, there is a wall at the top. And then the free stream, instead of being a uniform free stream, it's a uniformly shear flow with the direction of the mean gradient being opposite to that of the boundary layer. And so now you have a multi-structure region at the interaction range between the boundary layer and the shear flow. There's production from the wall, there's production from the free stream. Whatever is produced is mixing and interacting. And what's happened to C epsilon there? Okay, so this is the facility, and this is what we get. Okay, so this is the C epsilon. This is the mean profile, the solid line. So you have the boundary layer, you have the uniform shear, and you have the intermediate multi-structure region. And if you look at C epsilon, that's the important part. You see the canonical one away from the two ends. You go to the canonical values, which are essentially uniform, but in the between, they're much larger. Okay, so I don't have time to go through much, but many of these flows, it so happen now that C epsilon, although it's not constant, can be connected to turbulence characteristics in this way, that it is a power, particularly an inverse power, -1 of the Reynolds number. So there is some hope that one might be able to connect the C epsilon beyond the constant level to some relationship that can be integrated into future models and advance, our predictability of complex types of flows. So I'm skipping a few things, and I go to the final conclusions that the dissipation parameter was found indeed to be constant. It's not the first time, but it's good to know that it's not a completely inapplicable type of assumption, but some parts of canonical flow, certain regions, they have that. Also, we found that many of these flows can be have a common characteristic where this dissipation parameter is related to a power of Reynolds number and can be connected. And I think I have to stop here. Thank you very much.
All right, thank you so much.
I compressed a lot of things there.
Well, I think in about 30 minutes you covered what I tried to cover, and I didn't do as good a job, but I tried to cover in about 14 weeks. So I hope those that haven't taken the turbulence course appreciate how much of a condensation of a lot of knowledge you put in the first maybe 15 slides. So thank you for the talk. I'm really curious about the slides that we missed, but I think I should give chance for some of our students if there's any questions.
While the questions are coming, I'd like to thank you as well. Indeed, a very comprehensive presentation. For the audience, please put your questions in the Q&A or in the chat.
I don't see the chat here.
Yeah, we will basically take care of that. I know it's harder to. We got a few people thanking you.
Okay. I thank you for attending. There is a rule of thumb that one slide per minute, but the topic, I mean, needed a lot of background. So although I only have 48 slides, that I would probably need 2 hours to give all of them.
Maybe I can start off with a quick question. So near the boundary, I guess, is where this scaling it's not constant.
Right.
Is there any hope where it can be resolved outside? I mean, here you say that there's a chance that it would scale with RE lambda, but very close to the walls. Is that something there's any hope for that, or?
Close to the wall. I mean, in this case, the example I showed, I distorted more the outer region. I did
Yes.
not distort. I don't know. You talk about boundary layers?
Yeah, if you go
In
back a
this
few slides.
intermediate region between two types of flows where this doesn't work.
Yeah, okay.
But in this example, near the wall, we recover the boundary layer structure because it was not affected significantly by the outer stream.
Yeah. All right. I don't see any questions coming in. I know it's 2 and a lot
There's
of the
the
students
question.
have.
Let me just say that, and then sorry. I think Dr. Emily is asking questions. Basically, sorry, George, did I interrupt you, or should I
No,
just?
no, go ahead, go ahead.
Sorry. So a great presentation. This is by Dr. Emily, our colleague. So he's asking, do you see development of DNS methods for realistic Reynolds numbers?
Yeah, this is, of course, a lot of activity in that to improve techniques and make larger computers. Also, commercial codes are used now for kind of DNS, not meeting the strict criteria. But it's also known, I mean, they have projections of the need for computer resources, how much CPU you need and how much time, how long it takes. And from the projections, of course, we can see there will be some progress, but there are limits also. And now we talk about, for example, modeling entirely with DNS a flow around a jumbo jet. We may be decades or centuries away from that. I don't know. But for other intermediate problems, I mean, parts of cardiovascular system, different other, uh, let's say, industrial kind of things where the Reynolds numbers are not very high, and not too many other complexities. We, I think it's foreseeable to see DNS. The other hope is the hybrid methods that allow, to separate regions, where you can do in lower resolution and other parts with a higher resolution. So to develop more and more of these methods to be able to couple them, and apply only the expensive method where you need it and not elsewhere.
Thank you. And if you have a follow-up comment or question, Omid, please unmute yourself or put it there. Perfect. George, sorry, go ahead. I was.
No, I don't have any follow-up questions. I was just saying that around 2, I know a lot of the students have to go to, they have TA duties and things like that, so that's why maybe they were rushing and didn't get a chance to ask their questions. But for those that don't have time to ask questions, if you want to maybe send me an email, I'm happy to forward it to Dr. Tavoularis. And yeah. So the seminar ends at 2, Hussein?
Yes, a few minutes after 2.
You recorded that, right?
Yes, so
Yeah.
basically, this is something that I didn't get a chance to ask you in the beginning. I think our secretary, she put it by default to record,
Yeah.
but if that's not fine with you, and this is just for the purpose of sharing with our own students and in our website, but if that's not fine with you, I totally understand it, and we can basically not populate and delete it. Please let me
Not
know.
really. I mean, there is nothing there. In fact, I was going to offer if you want me to send you my slides.
Yeah, no, we
to keep,
basically
because I
recorded.
didn't talk about many of them. Yeah.
Okay, well, that would be actually great. I think Dr. Choueiri and others in the Floyd area, they can basically use that in the classes, and at the same time, it can be a complementary for the recorded presentation.
Yeah, because I mean the material, at least the first half, is material used. I mean in many textbooks, but not in the perspective. I have put a personal perspective into that. So so there is an approach. Although the material at the end, you could say it is. Presented, I mean, for quite a while. I mean, the modeling and processes and the logic on that. But I try to extract, the rationale or how to rationalize why this is done. So I think that might be useful for educational purposes.
Definitely, definitely.
Yeah.
Well,
So
thank you very much again for this
Okay,
presentation.
my
Really
pleasure,
appreciate it.
and I appreciate that you invited me.
Thank you. And George?
Okay.
yeah, so for those that want to go, I think this would be it. I just wanted to comment something with Dr. Tavoularis, but I guess the talk is officially over. But I just had a quick question out of curiosity.
Yeah.
Today I learned why we don't usually use the word octopi, and that's because octopus comes from a Greek sense, where the I for summing comes from the Latin. And I was just curious why a lot of the terms you came up with were Latin rather than Greek based.
Well, I feel that people connect more to the Latin on this end. So, and the Greek grammar is a bit more complex, so people are more familiar maybe with the Latin. Yeah, I don't know.
All right.
If I put the Greek words, that would be a bit awkward. I mean, if you are not familiar, with the language. But
All right.
also Latin has been used in throughout, the Enlightenment, and Renaissance, the scientific language. Newton wrote his book in Latin. You
Yes.
see, I mean, to write in Greek would have been, who is going to read it? I don't think they knew enough to do that. But the Latin was used until not long ago. This book I mentioned by Lucretius, which is an extraordinary book written more than 2,000 years ago. It was in Latin, and it was used as a Latin textbook. It's written in very good, high quality language, as a textbook. But then religious establishment found that this was related, to pagan philosophies and different approaches. So it was a bit suppressed and then resurfaced, and you'll be surprised how much detail it says about topics we consider modern.
Yeah, I'm curious about maybe
I mean,
I'll
the
try to find
description
it.
of Brownian motion is almost a modern scientific description, you see. Even talk about atoms that explain, besides the atoms of the material world, he has a certain second kind of much smaller atom, what they call atoms, which explain the mental activity, of people, and which all are recycled with death, and then the purpose of the book was to tell people, don't be scared, when you die, whatever you have is going to turn into something, other part of material, yeah.
Oh,
That was the
all right.
intention of the book. Yeah.
I'll try to find it. All right. Thank
Yeah.
you so much,
Okay.
Dr. Tavoularis, and thank you all
Okay.
for attending.
Thanks again. So bye.
Bye. Have a good day.